Hi everyone, welcome to another episode or like a video where I explain another paper or like try to tell my own understanding about it honestly. Today we're going to tackle a paper called Discrete Residual Loss Functions for Training PINNs, Physics Informed Neural Networks. This is a paper by J. Rishi, Sumant Kumar, Azhar Ghafoor and Deepak Subramani, and this is a paper by IISc Bangalore. Before we start, I just wanted to say one thing. In a sense of, I don't know how many people will see this video, but the ones who are seeing this, sometimes I know it's like on a philosophical note in a sense, but sometimes you feel that whatever effort that you're putting in, you are not able to see results of it because that validation factor takes a long time. And me personally, and many others, I believe, tie their own idea of success to just external validation. And for all the people who are trying every day to get that, all the best. I am too, and all we have to do is just put our bit every day. That is all. So let's begin. Basically, what this paper says is to understand pins in a much more logical way, in a way which is much more understanding apart from the traditional way pins are understood. Now, when we talk about pins, there's usually only the factor of automatic differentiation. While solving equations which have higher differential equations like derivatives up to degree 2 or 3, we usually use automatic differentiation, and that causes a lot of compute issues in a sense. Pins on their own have two types of loss functions. First is the boundary loss, and the second is the PDE loss. The PDE loss is the type of loss that actually keeps you in place and actually helps you understand the world in a much better sense. For example, if I want to carry out an experiment on fluid dynamics, which has on a very huge pipe, the PDE loss will be able to regulate the natural laws of physics. For example, conserving momentum at every point. So it helps us to be sustained within the laws of the nature, laws of the physics. So that's why one advantage of PIN is that you don't need a lot of training data set to actually train the data. Instead, we actually use already existing physics laws to train it much better in its understanding. In this paper, they have introduced an alternative or a better way to have that PDE loss. In this case, we have used an FVD loss, FVD, my bad, finite volume discrete loss. We're gonna come to that in a short while, but I just wanted to explain the second part of the loss as well. The PDE loss is the first loss. The second loss that is calculated is the boundary loss. The boundary loss is a simple, in a sense, mean square error loss to some degree, and this loss is only specific to the question at hand. So there are two types of losses that are working together. First is the PDE loss that regulates and maintains the normal structure of the environment according to the laws of the physics in a much grander scale. For example, we always have to make sure that gravity is towards downward direction. Like, you get what I mean? The kind of understanding that is fixed by physics laws in a large scale, conserving momentum, conserving energy. On the other hand, boundary loss is specific to the question itself. This is where we define a snippet or define the boundaries in which we are talking, in which the question is concerned about. And these are the two types of losses we are dealing with, as you can see over here as well. The loss for the entire pin system is comprised of two types of losses, the PDE loss and the boundary loss. And at the moment, when we calculate these, we use automatic differentiation to do so. This is a kind of differentiation process that actually takes place in every epoch, and it is very compute heavy because we need to calculate the pinpoint derivatives up to at least second degree at each specific point in that boundary area. So that leads to a lot of compute. That's the main thing. Now let's get on to the finite volume loss, something which is proposed by this paper itself. What they want to make you understand is a very simple case scenario that we usually used to use in physics in our high school, in like 12th or in first year of college in a sense. I'll give you some understanding. Hope you see this diagram. As you can see over here, we have taken this entire pipe in a sense. We're considering a fluid dynamics problem only. So of course we have an entire pipe and we take a snippet out of it, right? That is what we used to do when we used to solve questions for competitive exams as well. Taking an entire area. Now, for example, in this type of example, my bad, I used the word twice. We're going to maintain the PDE loss for the entire environment, while we'll only maintain the boundary loss for the snippet that we require for the question itself. In this case, let me just come to it eventually, you'll understand. And then it took me around 2-3 days to actually get this paper. But let's just understand each of the terms very carefully in a sense. As I told you, PINNs don't need a lot of simulation data because we rely a lot on physics laws. But on the other hand, in this case, for this example, we're going to use the Navier-Stokes equation, and we're going to define many terms which are pretty common, but it is something that we rely on for this problem set only. For example, the advection term, which is basically the fluid and the fluid direction and the flow of the fluid in which it travels. The momentum along the flow, that is the advection term. Second is the diffusion term, which is how the fluid smooths out, or the viscosity, or its nature of resisting movement. Now what's unique to this problem is that using FVD loss, we're going to define a rectangular grid in a sense, which maps onto the current problem, and then we are able to understand the situation much better. Like I said last time, I'll just come to that just a minute. So considering that we are going to define a flow-based or a fluid-based problem, we first need to define the upwind scheme, or define the areas where the fluid is moving using coordinates. Instead of actually getting a pinpoint derivative, we're just going to map out a grid on which we're going to calculate averaged out values. You get what I mean? So like instead of actually finding derivatives or an exact pinpoint that needs a lot of compute for calculating derivatives up to second degree, we're going to instead define a grid over which we're going to perform averaged calculations. So in this case, this means the east face. That means the face between the center point and east. North face, south face, and then the west face. Of course, we can also define and see which direction the flow is being with the positive values and negative values. The P being the central point, and this is the upwind scheme for advection terms. That means in the direction of the flow, right? So now that we have understood the basic structure of defining the problem, now we'll come to actually solving it. For, of course, using the gradient operator, in this case, in a normal PINN, we would have to actually find out the derivative at that exact point. But instead, in this case scenario, we're going to use this central difference scheme to find that derivative. This central difference scheme, in a very normal sense, in a very common sense, can be when we have a problem as defined as so, the flow going in, then the flow going out. Simply enough, to understand what exactly was in that snippet is to just subtract the outer flow, the flow going out from the flow going in. So that's what we have used in a very basic sense. That's why it's the central difference scheme in which we calculate this equation. On the other hand, for carrying out the differentiation of the second, or like differentiating once again, or carrying out the second derivative, we're going to use this equation. As you can see, this is still just an extension of the previous term. We're just gonna subtract the middle values twice and then subtract it by the square of the x values or the y values accurately. This follows the general trend of just finding out the out minus the in, and then of course making sure of any sort of extra values that is left from inside, if you get what I mean. To like, this is being subtracted just to mediate the extra flow that is left from calculating any sort of flow twice. I'll repeat, this is the kind of extra term which is left after calculating the flow twice, so we need to like subtract it out. And the residual loss in this case is calculated as the mean of the square of the finite volume discrete residuals at all interior points. So in a very common sense, or like in a very basic sense, instead of actually calculating the differentiation or the derivatives at an exact point, we want to instead use these formulas, which are much less compute heavy because they're essentially simple algorithmic formulas. So that saves a lot of compute. Now, like I said, we want to define the grid-based training procedure. But before we get to that, I want to clarify that in this paper, they propose an idea that redefines the PDE loss, but the boundary loss itself remains the same because that's basically just a MSE loss in a fancy package, but that part remains the same. Now, let's get on to the grid-based training approach. Like I said, we usually define the boundary points, and those are called as the domain collocation points, and the loss is calculated as so. And the Latin hypercube sampling is usually used in pin training. I myself don't have much idea about this point, but I hope to learn it eventually. But this section actually describes the rectangular grid as I told you before. So let's just compare the results and understand the difference between the FVD loss, which is proposed in this paper, versus the automatic differentiation loss as proposed before. Now, of course, to calculate this, we are going to define a much more simpler problem at hand. We're going to define a neural network with two trainable parameters, and that's all. And we're going to calculate the PDE for the same, and we're going to use it to solve a partial differential equations with AD loss and FVD loss. What we observe is that the AD loss requires a deeper network compared to the FVD loss, and the AD loss involves a greater number of matrix multiplications compared to the FVD loss. So that shows that it is much more computationally inexpensive. It is much more cheaper. Now, on the other hand, faster convergence, that means we're going to hunt for fewer iterations that are needed. Again, when we look at the results on the other page, we do observe that the primary alteration is the loss function pertains to the residual term, and also in this case we are going to use the one-dimensional Laplace equation for the test case. And as defined before, in this case we are going to investigate a network architecture comprising two neurons and two trainable parameters W1, W2, and the network is structured with a single layer. In this entire section, we're just going to calculate the same as defined before. My bad. As defined before. And what we learn from this as well is the efficiency of learning for a neural network through backpropagation depends on the characteristics of the loss function. All in all, in this section as well, it is proven that we do use and we do achieve a faster convergence. Now let's get on to a much more beautiful example to understand it much more better. I do understand that the last page was a blur to me as well, but this helped me understand much better. In this case, we can see that the blue one is the discrete and the green one is the AD. What we observed using discrete loss was that it had lower amounts of plateaus or false minimums. Instead, it went on much more smoother, and without having many plateaus, we avoid a lot of false global minimums. And on the other hand, the AD loss had a much higher chance of getting stuck in a local minima, and that actually improves in this case. Um, so yeah, like I told over here, the ADA network exhibits more plateau regions compared to the FVW network. And we're now heading on to the last part in a sense. A lot of it actually covers it in a pretty simple way. All of these are solved questions on very hyper-specific problems. Like in this case, we can see the difference. These are all types of the questions. And as you can see, the difference of epochs needed. These are all which are compared over time as well. In the case of questions with a higher Reynolds number, that is a much more unstable flow, the FVW, the FD, my bad. The FVD loss performs much better on higher Reynolds numbers questions compared to AD. And let's move forward. In this section as well, we have also defined new type of question. These are all defined in the table itself. In this case, we have the lid-driven cavity, and here we have defined the conditions in which we are actually training this. So let's get on to the one page. Now at this point onwards, if you have still made it, I want to discuss the trade-off of this paper. Whenever I discuss a paper or whenever we read a paper, we usually see that the method described in the paper itself has a very positive side. You see all of the best things that come out of it, and then you feel, why isn't it standard enough? Well, from now on, I'm going to focus more on the trade-off itself. That there must be some loss for any new architecture. So in this case, the FVD loss loses the flexibility, cause in every sort of new problem, we need to define the grid effectively. Like in the case of a flow-based question, the rectangular grid works well. But in any sort of other question, we need to redefine the grid every time. So we lose the compute or we lose our own mental thinking to define that grid and to define all of those faces and to define what criteria to take care of when defining that grid. So this is one of the more disadvantages of this approach. The automatic differentiation takes longer, but it is problem agnostic. You can apply it directly on any sort of issue because it actually calculates the differentiation at that point. And of course, we do understand that FVD losses works much better on higher Reynolds number flows, that is much more turbulent flows. But in the case of AD, it works like a charm on laminar flows or flows which have a lower Reynolds number. So there's no need to use it in that case. So let's move forward. This is the same thing where I mentioned about the Reynolds number. And this is the section where we talk about the complex symmetry and that rectangular grid issue. Like in the cases where we have a much more complex geometry, we need to redefine the grid itself, and that loses a lot of flexibility. And in the conclusion for this entire approach and the future work is, of course, gaining that flexibility again and to just find out a way to actually define a grid or define a structured formula that actually is problem agnostic eventually. And that is it. This paper was by IISc Bangalore, and these are the authors of the paper. And thank you very much for watching. I do understand that this paper was much more physics oriented and much more as an application of ML, but I wanted to dive into a much more deeper paper because I like that. I mean, of course, this channel is basically just an extension of what I want to do next, and I don't pertain to any sort of like pressure in a sense of what I need to read next. I'll just give like a brief. My next video will be on diffusion models and using diffusion models with time series forecasting, and post that we're going to tackle much more famous papers which are going nowadays, that is JEPA and also nested learning. But this is like the rough roadmap in a sense at the moment, but that is it for today. Thank you very much for watching, and good night.